Okay, so now let's go over the answers. And even though I gave them to you in like little groups that gave very similar methods of solving them based on the information that you were given, I'm going to go over them here in alphabetical order because that's how the sheet is laid out, and that was the way I solved all my answers. So let's go through the first one. So A. So you know the two forces. So from that, you can see that this thing is balanced. And since it's balanced, the net force is 0 and the acceleration is 0. So the only thing you really have to solve for is the mass. And since the mass equals the force of gravity divided by the acceleration of 10 meters per second squared, you end up with 0.1 newtons divided by 10. So you're going to get 0.01 kilograms. And a lot of times people struggle with this sliding the decimal point thing. So use your calculator. You guys have your calculator accessible. Divide by 10 and just always make certain you get it right. So number 2, you were given the mass and the acceleration. So from the mass of 10,000 kilograms, you can multiply it by 10, get 100,000 newtons. And I did go work through this example when I gave you some instructions, but I think it's helpful to go over it again. So since the mass times the acceleration equals the net force, we know that it's going to be 10,000 times 8, which is going to be 80,000 newtons. The reason we know it's down is because the acceleration and the net force are in the same direction. So in order to take a look at this, we know that there's 100,000 newtons down here for the gravity. We know overall this one has to be larger than the F air by 80,000. So that would yield this to be 20,000 up. And if we look at this, 20,000 up and 100,000 newtons down, we still end up with a net force of 80,000. So that's always a good check when you're finishing these up, just to make certain. Did you flip a sign? Did you have the wrong one being larger? Just take on second glance at this, because this is the most common mistake that students make. They'll make this one to be 180,000, and then your net force is up, which says that the elephant is accelerating upwards, which might be kind of challenging. Okay, letter C. So we were given mass and acceleration. Again, I'm going to take the mass and multiply it by 10 in order to get the force of gravity, or the weight, which is going to be 8,000 newtons, and it's going to be down. Since we know the mass and the acceleration, we can find the net force. So we're going to take 6 times 800, and that's going to give us 4,800 newtons. And the direction is up because the acceleration is up. So we know that downwards it's 8,000 newtons. The overall net is 4,800 newtons. So that tells us the upward force must be 12,800 newtons. Pause it, make certain that makes sense to you. Write down whatever you need to ensure that you are good with that. Then letter D. This one, we have looking at the normal force and the gravity force, it's balanced. So there's no net force in the up and down direction, but we have a leftward force with no opposing right force. So that tells us that our net force must be this 9,000 newtons going to the left. We're given the force of gravity. From that, we can find the mass, and we do that by taking the force of gravity, dividing by 10, and we get 1,000 kilograms. And then we're left with solving for the acceleration using F equals ma. We rearrange this equation. We have 9,000 newtons divided by 1,000 kilograms, and we end up with 9 meters per second squared. And it's also to the left because our net force is to the left. So then letter E. This time we're given a slightly different variation on the original information, but again, we're doing the same thing. So we have the mass is half a kilogram, and we know if we multiply that by 10, we're going to get the weight, or the force of gravity. So when you multiply that by 10, you get the force of gravity is 5, so it's 5 newtons. We know that the net force overall is 124 newtons to the right, so there is no leftward force pulling it to the left in any manner. So we know that leaves us that we can just copy down this 124 newtons to the right up here. It must be balanced, so it's 5 newtons gravity and 5 newtons upward for the normal. And then the only thing left to solve for is going to be the acceleration, and we're going to use F equals ma. So when we've rearranged that for A equals F over m, we have 124 newtons to the right. The mass is 0.5 kilograms. When we divide that, we get 248 meters per second squared. And we label it with a direction to the right because that's the same as the direction on our net force. So then with F, we are given our upwards and our downward force, and those are balanced. So we know there's not going to be any net force in that direction. We're given that the acceleration is to the right, and that kind of goes along with the fact that we know that there's a rightward force. But first, in order to figure out anything else, we're going to have to solve for what the mass is. So we know what the force of gravity is at 9,000 newtons. We know we can divide that by 10 meters per second squared, which is G, and end up with 900 kilograms. So 9,000 divided by 10 is 900. So we're going to use the Newton's second law of motion. Net force equals mass times acceleration. Multiplying that 900 kilograms times 1.5 meters per second squared, the direction is to the right. When we solve that, we get 1,350 newtons to the right. So that is our net force, remembering our directions for acceleration and net force are the same. And then you can fill in the F applied as being 1,350 newtons. And there is no force on the left. So even though this man is drawn as being pushing it, but he's pushing it to the right, the free body diagram would be the same if he could apply the force at the front of the vehicle and pull it along with him. Okay, so the last row. So G, we were not given any of the forces on the free body diagram, but we were given mass and acceleration. So the first thing we can calculate is the net force, which is equal to mass times acceleration. So 15 times 0.5, we're going to end up with 7.5 newtons to the right, the same direction. Looking at our free body diagram, knowing that it's 7.5 newtons to the right, we can fill in our F applied here right away. We were given our mass, but we weren't given our weight. So we can use weight equals mass times gravity, which is 15 times 10. So we get 150 newtons down. So that's how we fill in our F gravity. And our F normal is upwards and it's balanced, so it's going to be the same. H, we are going to have, we have all of our forces on our free body diagram filled in. We can see that the up and the down are balanced. There is a net force to the left, this force of friction here. So we know that we can fill in that right away. The net force is 100 newtons to the left. So we can calculate the mass because we know the weight. So the mass is the weight divided by 10 meters per second squared. So we're going to get 600 divided by 10, which gives us 60 kilograms. From that, we can solve for the acceleration. Acceleration equals net force divided by the mass. So we've got the net force of 100 newtons to the left, 60 kilograms, and now we know that the acceleration is equal to 1.67 meters per second squared to the left. I rounded it to 1.7 here, meters per second squared. And then the last one on the sheet is I. So we have mass and acceleration and one of our forces. So what we can do is we can start out with our mass. We can solve for our net force is mass times acceleration. So we've got 2,000 times 2, which equals 4,000. So we know our net force to the left is going to be 4,000 newtons. By looking at our free body diagram, they gave us that the rightward force was 14,000 and our leftward force was 10,000. And that allows, our rightward force was 14,000, our net was 4,000, and that allows us to solve for the leftward force being 10,000 newtons. I did that with 14,000 minus 4,000 equals 10,000 newtons. Since our net force and our acceleration is to the right, our rightward force has to be larger, and it is, and it's larger by 4,000, so that makes sense. Finally, we know that our upward and downward forces are balanced, but we have to find what our weight is since they gave us the mass. 2,000 kilograms times 10 meters per second squared equals 20,000 newtons. So the normal force is going to be 20,000 newtons, as well as the gravity force, because they are balanced. So ladies, what I'd like to see you turn in for this assignment is I would like to see what you fixed, what you corrected, and I'd like you to write one statement on what did you not do correctly, maybe as you were working through these, that you really do need to pay attention to. So even if you just write a statement on the side of the sheet of paper, on another sheet of paper, what is one, maybe two things that you need to be careful of that makes it really easy to make a mistake on these? Okay, I will be returning with the next video, which will be in the next topic.